So let's continue with Gennadiy. The left? Yeah. Okay. So let's continue with Gennadiy Burlak. He's coming from Universidad Autónoma del Estado de Morelos, specifically the Centro de Investigación Ingeniería y Ciencias Aplicadas, and he's going to talk about solitons in periodic and quasi-periodic optical lattices.
Okay, thank you. First of all, I'd like to say many thanks to Natig, Professor Natig, Atakishiyev, organizers, and that Natig has a lot of friends. And therefore, I'd like to say buenos dias, buongiorno, guten morgen, добрый день, доброе утро to everybody. Okay, my topic, it is about solitons in periodical and quasi-periodical structure. The case in that the structure of soliton and typical soliton, it is well investigated in case of one-dimensional structures. In this case, the problem of solitons can be resolved very clearly and an analytical way. But unfortunately, it is not the case two-dimensional and three-dimensional. Two-dimensional solitons has other structures, and therefore three-dimensional soliton, it is very difficult to obtain any information. Only numerical calculation we can obtain. But first, I'd like to remind you where.
No, it's here. It's on the right and on the,
okay. Okay. This is okay. This is a short, brief outline of my talk. First of all, I'd like to say about something about under-introduction, what is Bose-Einstein condensate. After that, about classical and quantum theory, that is about more advanced model structure formalism to obtain the information from soliton. After that, what is the quasi-periodical structure of the potential, this is Penrose scaling. And after that, if it's possible, obtain some analytical result in case of two-dimensional soliton. It is variational approximation. After this, solution of equation that we obtained here. And after that, numerics. It is results that can be obtained as a result of evolution of solitons. After that, a little of recent solution. But in general, the publication about soliton, it is huge number of publications, therefore clear. It is not simple to obtain something about this. After that, conclusion and reference. But before, I'd like to say a little bit information about what is the Bose-Einstein condensate. In general, as we know, is and exist in nature only two types of particles, of two-particle statistics. It is Bose-Einstein. Bose is the statistic. That is, difference is very simple, very small. Only in case of Bose, statistic is written minus. In case of Fermi-Dirac statistic, this is written plus. This is only difference, a little bit. But that small difference generate a very large difference and evolution and dynamics of this excitation. First of all, this is a written formula. This is very known from statistics. It is written the number of particle n with except of statistics. Okay, this is energy, and mu is a very important case that is written chemical potential. Energy, normally, it is connected with K, with wave number that is written here. It is clear for electrons and bosons. It is written here normally. And after that, clear we have to we have to choose to put from this case to other case, asymptotical case. Asymptotical case. This is changed to the sum to integral, and in this case we have obtained that it is possible as, to do with simple case, but is not. At least we have to see that for k equals 0, the energy it is 0. Okay, if we do not take place to this case, we obtain the integral in this form that is written here. This case it is volume. This is volume, and C it is some constant that had dependence from temperature and chemical potential. This is integral. In this integral we have to give attention from for one case. Mu chemical potential should be negative. Before it is not negative, at least it is 0. We can obtain, and for C equals 0, we have obtained some exception. Is this exception? This means that in this case it is some exotic phenomena. Really it is, and therefore to obtain some critical temperature that can be obtained with this expression, we have to put mu equals 0, and after that the Bose-Einstein condensation can be obtained and simple form. Simple Einstein condensation is that for temperature that is less than some critical temperature that is written here, the number of particles should be written in this form. That is number of particles for energy that is positive and number of particles for energy that is equal 0. It is stage of Bose-Einstein particle, that is new form of particle, and from physical point of view it is obviously why boson can be concentrated, and when a ground state it is no problem for condensate. What is the critical temperature is written here, and number of particles that can be in the ground state or condensate is written here. So therefore, if temperature it is equal of T0, we obtain that number of particles should be all equal n in this case. This normally named Bose-Einstein condensation, but a lot of questions is be generated for this consideration. Only boson or particle can be considered here without any interaction. This is only model that is simple to consider for resolution, for obtain some result, for example, what is critical temperature, is it possible? But after that, when we have this answer to this question, it is interesting to resolve this equation for interaction bosons, that it is not simple. After that, because energy is very small, we have to give attention, a lot of attention, to the quantum cases, the quantum effects. Okay, therefore, it is a lot of time to obtain, some effect, some study, experimental study of Bose-Einstein condensation, and it is very important that in 1996, see these guys obtained the Nobel Prize in Physics to observe experimentally the soliton. And therefore, it is the prediction of solitons, no soliton, Bose-Einstein condensate. It was a lot of years before of this observation, and only observation. It is demonstrated only in this year. Okay, but next case it is how to right now it's possible to study and to discern the quantum theory of Bose-Einstein condensate. In this case, clear that we have to say something about the wave function of the condensate that is written here. Number of particles, it is defined the normal ways that is written and in physics and theoretical physics, and therefore we can obtain this form of energy that is written here. First case is kinetic energy, potential energy, and here is other important particle that is nonlinear particle. Therefore, in this case, we have obtained in our model the interaction between bosons that it was not done before a lot of years. After that, the simple consideration, simple mathematical structure, we can obtain this nonlinear Schrödinger equation. It is well known nonlinear Schrödinger equation, and any theory and an important case that is written. This part, it is normal linear Schrödinger equation, but it is because the interaction between boson, it is included. And normally this equation is applied later. In case, as I was said before, one-dimensional case is studied very good. And it is very famous theory is considered in this case, and that gave us results that there are soliton, normally soliton, and a small very perturbation. But what will be a two-dimensional case? Two-dimensional case is indicated here. We have said this is dependence on the plane X and Y coordinates. And the nonlinear part is written here. This is potential that normally we have to include in our model. And therefore, the first question, is it possible to obtain some analytical solution of this equation? Unfortunately, not. More exactly is can be said that is yes. It is only can be obtained some solution for soliton. It is tau soliton, but unfortunately this solution is unstable. Therefore, it is not give us too many information. Okay, after that, it is obtained. The solitons in two-dimensional case have only two scenarios to be for dynamics. Dynamics is the following. First case, it is collapse of the soliton, and two-dimensional case. Other case is decaying of the soliton. What is the boundary? Boundary, it is tau soliton, therefore it is the boundary soliton, it is unstable. Therefore, a little perturbation to this form of soliton, we will go to the dynamic of soliton, it is collapse, or it is decaying. Okay. The question after that is it possible to stabilize this instability of the tau soliton? The question or solution is yes. We only have to apply some potential that is written here, and a lot of works. It is shown that in this case it is obtained the stable solution of the soliton. Again, unfortunately, in this case, it is not possible to obtain any analytical form of solution. Only numerical solution of this dynamic can be applied for investigation of this model. Okay. Right now, I'd like to say something about solution. If we have in this sum only one member, that is cosine, normally R is written, R it is radius that normally is well known. In this case, we can obtain only harmonical potential. In this harmonical potential, really, it is possible to obtain stable form of the soliton. Soliton, it is a ground state, but clear that the soliton have a little bit dynamic of minimum of this potential. It is well known. But right now, it is interesting. What occurs and other type of potential. Other interesting form of potential, it is written here, it is quasiperiodical potential. quasi-periodical potential, in this case, K, that is written here, and important that normally M is equal 5. And in this case, I'd like to focus on this type of potential, what will occur with solitons and quasi-periodical potential. Okay, this is again nonlinear Schrödinger equation. What type of coefficient I will talk about? Only for case when J it is negative. In J it's positive. It is normally, it is not very interesting for soliton, but in J is negative, it is attractive case when soliton is undergo the collapse. Here right now, a little bit illustration about what is collapse. First picture is written the initial state of the soliton. After that, soliton, if we have suitable form, is a little bit more, and after that, collapse occurs. It is a solution obtained by numerical method, but therefore we can obtain, in this case, the soliton is very high, but is very thin. In this case, clear, but the norm of number of particle soliton, it is constant. Other case, it is important to say here. The nonlinear Schrödinger equation, it is normal equation, and that is a partial different equation. Therefore, we have considered first any conditions, any initial condition, any state, but it is as initial state. Therefore, at the equation, it is what is fundamental state of the soliton. Fundamental state can be obtained because it's nonlinear equation from any initial states when it is stable with respect of small perturbation. For this case, exists special approach how to obtain the fundamental state of soliton, and therefore we later can obtain a study what is the dynamic of soliton. Okay, this case again it is collapse of soliton. This is I heard about the only the town soliton is soliton that normally can be obtained. What is form? That is form of Gaussian because the system has a spherical symmetry. But again, it is for this number of coefficient, and this soliton, town soliton, has a special threshold. If the amplitude or n particle is larger than this form, the soliton undergo collapse. It is less, the soliton undergone to decaying. Okay, this theory normally can be applied to nonlinear optics. Before in nonlinear optics, the structure of equation for the electromagnetic amplitude has the same form. Okay, right now, what about the potential we have applied here? First, it is soliton and other form of potential that is I mentioned before. That is normally periodic potential, that is when written and when studied. It is the potential quasi-periodic. And after that, it is quasi-periodic, but for other case. One can see that here, it is a rather interesting structure. It is not periodic. It is not random. In this case, it has a very special structure. Okay. After that, what I talk about? After that, this is results that allow to study the nonlinear Schrödinger equation and two-dimensional case. But with potential, this potential can have dependence on the time. What type of this dependence on time can be? It is normally the periodical time, and therefore the potential can to breathe in this case. After that, what is important? Other case. This is normally case coefficient nonlinearity that use in nonlinear Schrödinger equation. G can be negative, but more case it is very interesting. Other type of nonlinearity, more greater type of nonlinear, and in this case, important it is where is the fact when it is negative, but it is always positive. Therefore, this effects is some compensating effects that occur in this case, and we hope that collapse of soliton can be stopped by other mass high type of nonlinear. Okay, again about quasi-periodic potential that is real here, and clear right now it is a good idea to observe what is the form of this quasi-periodic structure. It is written here with detail. It's quasi-periodic case, and this is soliton that was observed. A little bit about quasi-periodical structure. The Penrose tiling, it is example of non-periodical tiling generated in a periodical set of prototypes. Periodic tiling I named after mathematician and physics Roger Penrose, who investigated this set in this year. The aperiodicity of prototypes implies that a shifted copy, it's important, the shifted copy of the tiling will never match the original. If we are here, it is very different from an original. It is other structure of the, it is not periodical. Okay, and for some case, it is five-fold rotation symmetry is written here. We can observe that it is interesting structure. It is not random, but it is not periodic. In this case, it is Penrose tiling that has many remarkable properties, and most notably, it is not periodic. It is interesting case that it is self-similar. It exists some formula that we obtain one part of this is potential from the center if we obtain some recursive procedure in this case. Okay, and in this picture we can observe the Roger Penrose in the foyer of the Mitchell Institute for Fundamental Physics and Astronomy, and the floor with the Penrose tiling. It is Penrose tiling, and this is Penrose. Okay, and right now, if it is possible, calculate something and analytical form. Normally, the main method that Penny applied for this science, it is the following. The Schrödinger equation, it is well known, that can be obtained from Lagrangian, density of Lagrangian that is written here. This is primary part can be obtained normally Schrödinger equation linear, but it is nonlinear part that produce a nonlinear part of nonlinear Schrödinger equation, and it is potential. If we have the density of Lagrangian, what next? We have to apply the Lagrangian, from Lagrangian, the Lagrangian equation. The first of all, we have obtained Schrödinger equation, and after that, nonlinear part. Okay, but it is that give us nothing because we can't obtain analytical solution. We can to study what is the property of the solution. Therefore, next part it is to apply variation approximation. We have to search for the solution of nonlinear Schrödinger equation with two parts of nonlinearity in this form, as written here. What is new in this part? Normally, the variation approximation is indicated with attention that normally soliton or Gaussian has symmetrical, not spherical, symmetrical form. Therefore, in this case, we can obtain this is width of soliton of Gaussian for x and for y. Normally, it is applied for when it is equal. But is it possible to obtain the solution when W1 and W2 it is different? One thing is written here, that is B1, and B2 is written here. That is phase, normally phase is equal, the same is equals always. Therefore, we can obtain, we have to use to apply for solution of nonlinear Schrödinger equation this form that more applied for quasi-periodical tailing that we have studied here, will study here. After that, we can obtain the standard technique. There's nothing new. We have to obtain the standard technical to apply to see is it something new or something wrong. We can obtain that if we apply the absatz of that is written before in this case, normally we obtain the number of particles conserved in this sign that is clear as it should be. And this can form, this is amplitude of soliton, and this is width of soliton, but in X and Y direction. Okay. After that, we have to apply obtain the Lagrangian equation. Unfortunately, the Lagrangian equation, it is very, very long. So long that I have not possibility to read this here. Therefore, but it is strongly nonlinear equation. What I have to do next? Next, I have to use some method to perturbation to obtain the dynamic, what is the dynamic of the solution for a long time. Therefore, I start to search for the solution in this form. This is complete solution of soliton. I have to separate in this form. This is nonlinear linear or zero order perturbation, or that is first order perturbation. Therefore, as is well known, I have to apply to this form to nonlinear Schrödinger equation is separate. Part with zero order, part with first order. This was done later. And for zero order, we have obtained this case. This is stationary case that is expected. It is not any dependence of the time. The solution, it is very simple. That is written here and has this form. It is important to see that here it is n minus 2p. N, as I remind, it is number of particles. 2p as 2p. Why it exists here? Normally, where n it is equal to p, it is threshold of the soliton that can be observed down soliton in two-dimensional case. Therefore, we can see here that for dynamic, it is important to see that n should be more than 2 pi. What about the first order? First order of equation is that solution is written here. Clear for case. It was applied that n is more than threshold of the soliton, and chi coefficient. Let me remind that first equation is cubic nonlinearity, and second equation that is written in nonlinear Schrödinger equation, it is named quintic nonlinearity. Quintic nonlinearity. It is coefficient of the quintic nonlinearity, and J normally it is normalized to put -1. Okay. Therefore, it is solution of first order. What is interesting in this case? We obtain that dynamics, it is not stationary solution because it is dependent on the time it is written here. M, it is difference that is written here, and we obtain interesting result that it is a dynamic system. Therefore, in this case, the first perturbation of nonlinear Schrödinger equation have one periodical solution, one periodical dynamic. It is written here, this solution. After that, for W, it is, let me remind that W1, W2, it is the width of soliton and X and Y direction. Again, M, it is more the threshold amplitude that is written here, and C2 and 1, it is normally some arbitrary constant that normally we can obtain for this type of equation. Okay. In this case, it is interesting to see that this system has the agent frequency. Therefore, M, that is written here, is have dependence here. If n, number of particles, it normally is fixed, therefore M, it is fixed, therefore it exists some agent frequency oscillation of this system. Other case, it is important to say that we have to see that number k, it is sign or coefficient of quantum nonlinearity, always should be presented here. If kappa is 0, a solution not exists. Therefore, we have obtained the solution only for cubic quantic system. Only in this case, quantic coefficient, quantic equation will compensate the cubic nonlinearity, and therefore we should should not obtain the collapse in this case. Okay, later. This is agent frequency are indicated here. This is one agent frequency and two agent frequency. Again, we obtain that n should be more than 2 pi, and k should be presented as quantic nonlinearity. Only in this case, this solution can be obtained. After that, that is little plots that show us the dependence of the value of agent frequency that is written here from n. Therefore, as we remember, agent frequency, it is n minus dose p. And it is width of soliton. This is written here. Okay, let me say one important thing about solution. This solution can be, no, Clarke, could be obtained on the paper. But there are a lot of calculations. Therefore, to obtain analytical result from the solution, I have to use the algebra simulation, calculation, and well-known Maple system. It is graphic from the Maple system. Okay, and this is steady state, and this is dependence of agent frequency. Right now, we obtain that this dynamical system that have two agent frequency. And what is dynamic? More interesting in this case. Okay. Right now, but linear approximation, it is interesting to obtain only the structure of solution. What is the agent equation? What is the agent frequency in this case? But later, what we have to do, we have to calculate to study the system. But it's not simple. It is not impossible to calculate with analytical solution. Maybe after today, I'd like to see if the structure of this solution, structure of this equation, can be written and form the Francesco form. Okay. But in this case, I'd like to say, because we have to study the nonlinear solution, nonlinear dynamic, right now I'd like to obtain solution, clear, this is the numerical solution, general dynamic, what will be for general widths of soliton, not for linear system, in general case. Okay, I have to say about initial state of the system. It may be different, but in this case, for example, in this case, it is very interesting, and we have used the stationary form that is written before. Okay, and right now that is the dynamic. Clear. If we have nonlinear equation and we can't resolve this equation, I have to investigate what is the effect behind of this equation. And therefore, after that, I can see the solution. It is solution and dependence of time. We can obtain that it is very interesting dynamic. It's clear, not more, but after that we have one peak solution. After that, it is interesting other case. It is the phase plane of this equation. We obtain the dynamic, it is rather complicated. After that, we can obtain. Right now, I will illustrate different fuzzy plays for this solution, and the question is this: okay, it is interesting, but is it can be obtained House here? Maybe yes. Maybe yes. After that, we obtain that it is dynamic of with respect to time, but it is the dynamic and phase plane. Sometimes it is maybe interesting and maybe have Algon structure, something like Lorentz attractor, but who knows? Okay, after that, the question is, because my potential have dependence on the time, and the other case, I have dependence, the system has two agent solution. Okay, if we have the dynamic of my potential, this that I have to change the frequency of the dynamic. With this frequency will be equal the agent frequency of this dynamic that in obtain it. This is something like resonance. In case of resonance, we can obtain it. This is written for resonance. The dynamic, it is more regular, but we obtain as in every resonance, we can obtain that it is more or less solution. That is written here. Okay. After that, we obtain this is other type of solution. It is again rather complex solution, but more or less it is located in one part of the fast plane. After that, it is other. Case of the resonance case, and therefore we obtained. In case of resonance, we have a very different dynamic that is written here. Okay, after that, if I have, maybe here. It is interesting. That equation, that normally it is variation approximation for symmetry soliton when W1 equal W1, if this solution still exists in any case. Yes, maybe see in case of resonance, we can obtain here that W1 is equal 2, and therefore it is line. In this case, sometimes for some parameter, we can obtain the well-known variation solution of variation approximation. Okay, and right now I have to say something about the recent work in this case. It is well known that solution, it was realized for atoms, rubidium atom, that are bosons. But in this case, it is observed that Bose-Einstein condensation can be observed for photon and optical microcavity. It is written here. In this case, it is the point of view physics is very interesting because photon, it is other case. It is boson, but mass of photon is 0. Therefore, what is with critical temperature, but it is experiment. It was realized. Okay, a little bit what's about the three-dimensional case. It is completely different case, and therefore, first question, what is the tools to study the simulation of this case? It is written Soliton. Soliton, it is in central intersection, but in three-dimensional case, it is not clear how obtain the amplitude of the soliton. We have to obtain only one separate approach. This is three-dimensional cases in this case. Bien. In this case, we can study the amplitude soliton in three-dimensional case only with color. This is central part, this with large amplitude, and we can obtain that here. This is smaller amplitude of the solitons. Okay, this is my conclusion that is written here. It is written all things that I that I had talked about, and important that variation approximation that is more advanced with two possibility to width of solitons leads to very strong dynamic. That is written here, and clearly main results can be obtained here only with numerical calculation. There are a lot of huge, not a lot of huge number of publications. Is written here is only a little bit. And finally, thank you for your attention.
Some time for questions.
Well, one of the properties of one-dimensional solitons is that when they collide, they eventually...
Yes, I understand. In case of one-dimensional soliton can be studied very detailed. For example, we can we can see more information from the book Francesca Collegiana. But in case of the two-dimensional soliton, it's not possible to obtain solution the nonlinear Schrödinger equation in analytical form. It is well known because the specific form, the specific effect of two-dimensional case that we obtain collapse of soliton for how nonlinear effect, even for very smooth initial condition. Yes. It is main difference for case of two-dimensional soliton and maybe, I believe, three-dimensional solitons too.
Can you have
rotation symmetry?
a B-soliton
Yes. It is, thank you, it is very interesting question. The collision of soliton, it is very interesting, and the question is it the same as one-dimensional case? Because in one-dimensional case, soliton can be passed, and after interaction will pass again, but with no change of the amplitude. In this case, exists various scenarios. Sometimes it is merged solitons. Maybe it is solution when soliton can be after interaction again to go in other direction with no change of form. It depends. It is not simple, in the case of as you remember, in nonlinear soliton and nonlinear solution, there are a lot of equations. For say nonlinear Schrödinger equation, it is one soliton. It is about. But normally, it is very different scenarios. They depend very strongly what type of soliton, amplitude of soliton is merging of soliton, and maybe other form that after interaction soliton can be passed. It is not theory about this case. We can only to check. We have to only to investigate by numerical method what be final solution in this case.
1 minute for another question, Robin.
It's not exactly a question, maybe a comment. Nonlinear Schrödinger is nonlinear, as you pointed out. Nonlinear Schrödinger is essentially nonlinear.
Yes, sure.
It means any solution, as opposed to linear equation, has singularities somewhere in the complex plane. And if you input the potential, which is an entire function, like a sum of cosinus, then there is no hope to find exact solutions. We'll only find approximate solutions. On the contrary, if you input for your potential, let's say a sum of Koch function, say localized, but Koch has singularities in the complex plane, then you will be able to find exact solutions. And similarly, when you undertake variational approximation and you input as an assumption psi equals some entire function of x and y, exponential x squared, exponential y squared, then again, this could be justified by physics. But from a mathematical point of view, you lose any chance to get a solution, an analytic solution. You must input some singularities in the complex plane, not on the real line. For instance, if you input a Gaussian, exponential minus x squared,
Yes, sure. Yeah, I understand.
nothing will come out. If you input 1 over cos squared, which has the same kind of
Yes.
decaying at infinity, you will win.
Yes, imaginary edges. This is a singularity. Yes, but to obtain something from the nonlinear equation, I have to say something about in which form I'd like to search for solution. Clear that it is a solution, the localized form, well localized form as Gaussian, and therefore maybe it's a good idea to study more other type of initial approximation. Maybe it is expected other effect here.
You can even do the opposite. You input potential equals sech square, let's say. Then you compute psi, and psi will be sech square. Self-consistent. I will explain.
Well, we can wait for lunch.
Okay, thank you very much.
So thanks again.